Imagine living inside a city that has been deliberately cut off from the rest of the world. No internet connection, no resupply trucks, no grocery deliveries, no municipal water authority, no hospital network, no banking system, no waste management contracts, and that city is moving through open ocean at 30 knots, surrounded by nothing but horizon in every direction, carrying 5,000 human beings who need to eat 3 times a day, every single day, for months. That is not a hypothetical. That is the operational baseline of the USS Gerald R. Ford, the most expensive warship ever constructed, a vessel that cost $13 billion and was designed from its deepest structural logic to function as a completely self-contained civilization, capable of surviving indefinitely without contact with the modern world. Most people, when they imagine a warship, picture weapons, the flight deck, the jets, the missiles, the sheer aggressive geometry of combat capability. But the engineers who built the Gerald R. Ford spent billions of dollars solving a problem that has nothing to do with weapons and everything to do with the most basic human requirement on Earth, the need to be fed, 5,000 people, 3 meals a day, every day, no delays, no excuses, in hostile waters, under operational silence, without a single external supply chain available to bail the system out if it fails. So the question that matters, the one that determines whether this vessel functions as a military force or collapses into logistical chaos within 72 hours, is not how many aircraft it carries or how fast it can accelerate. The question is this: when the Gerald R. Ford is 600 miles from the nearest coastline, operating under communication blackout, with no port in range and no resupply scheduled for weeks, how does it feed 5,000 people without breaking? The answer begins not in the galleys, not in the refrigeration holds, not even in the provisioning manifests that are loaded before deployment. It begins in the foundational design philosophy that governs every system aboard this ship, which is that every critical function must be self-generating, self-regulating, and self-repairing because the ocean offers no second chances and no external help. The Gerald R. Ford was not simply built to carry food. It was engineered to create the conditions under which food can be stored, prepared, distributed, and consumed at industrial scale, continuously, across months of isolation, by a workforce operating under extreme fatigue, psychological pressure, and the constant low-frequency awareness that if the systems fail, the mission fails first, and the people suffer second. This is constraint-based engineering at its most serious. Every design decision in the food service infrastructure of this carrier exists, not because it is convenient or cost-effective, but because the alternative, a breakdown in food supply, would destabilize 5,000 people within days, degrade operational effectiveness within a week, and potentially compromise the entire mission within a month. Human beings under sustained caloric deficit become psychologically unreliable, physically degraded, and institutionally ungovernable. The engineers knew this. The admirals knew this. And so the food system aboard the Gerald R. Ford was built not merely as a logistics solution, but as a psychological anchor, a daily repeating signal to every person aboard that the ship is functioning, that the order holds, that the civilization inside the hull is intact. If you lived here, 3 meals a day would not be a comfort. They would be evidence that the system is working. The scale of what must be accomplished every single day is worth pausing on, because civilian logic cannot quite process it without friction. The Gerald R. Ford feeds approximately 18,000 meals per day, not per week, per day. To achieve this, the ship carries provisioning loads that are measured not in days, but in months, with cold storage capacity that rivals a mid-sized commercial distribution center, dry goods storage systems that must account for humidity, temperature variance, pest control, and structural vibration, all of which behave differently on a moving ship than in a land-based warehouse. The provisioning process begins weeks before deployment, when supply officers work through detailed consumption models that project not just how much food will be needed, but what types, in what ratios, calibrated against the known caloric requirements of a workforce divided between administrative personnel, engineering teams, aviation crews, and special operations elements, each of which has different physical demands and therefore different nutritional requirements. A pilot flying 6-hour combat missions burns calories at a rate that is measurably different from a sailor managing paperwork in an interior compartment, and the provisioning system must account for this at aggregate scale. Getting it wrong, over-ordering heavy proteins and under-ordering complex carbohydrates, for example, does not just create waste or dissatisfaction. It creates a slow-building nutritional deficit across thousands of people who are already operating under physical and psychological stress, and a deficit of that kind, distributed across a crew at sea, compounds quietly until it manifests as degraded performance, increased error rates, and fraying psychological resilience. Here is what most people never consider. The food system is not just a logistics problem, it is a human performance system. And human performance, when 5,000 people are living and working inside a sealed metal environment with no escape, is the most critical system on the ship. The cold storage infrastructure required to sustain this is substantial enough to warrant its own analysis. The Gerald R. Ford maintains multiple refrigerated compartments operating at different temperature bands, deep freeze for long-term protein storage, standard refrigeration for perishables with shorter shelf windows, and controlled cool storage for produce and dairy products that require precise humidity management in addition to temperature control. These systems run continuously, drawing power from the ship's nuclear reactors, and they must do so without interruption regardless of what is happening on the flight deck above them or in the engine spaces below. The failure scenario here is not abstract. If the refrigeration systems lose power or experience mechanical failure during an extended deployment, 6 weeks from the nearest port, mid-ocean, in summer heat, the ship faces a cascading food loss event that cannot be reversed. Proteins begin degrading within hours of temperature excursion. Within 24 hours of a sustained refrigeration failure, the cold storage holds would need to be evaluated for total loss. The provisioning officers would then be managing a crew of 5,000 people with significantly reduced food stores and no possibility of emergency resupply within any practical time frame. The psychological dimension of this failure is not about hunger, at least not initially. It is about the knowledge that the system has broken. It is about the visible evidence of disorder in an environment where order is everything, where routine is the mechanism by which thousands of human beings maintain psychological coherence across months of enforced isolation. The food service teams aboard the Gerald R. Ford are not simply cooks. They are, in a meaningful operational sense, the daily administrators of crew morale and psychological stability. When the meal is served on time, hot, and in quantity, 5,000 people receive a subconscious confirmation that the ship is intact. When it is not, the confirmation runs the other direction. This is where the engineering of the galley systems themselves becomes relevant, because the Gerald R. Ford was not designed with conventional shipboard galley logic. The ship operates multiple galley facilities distributed across different deck levels, each capable of functioning independently, which is itself a critical redundancy design. If you were to lose one galley, fire, mechanical failure, flooding, the others must be capable of absorbing the additional load without collapsing the overall meal production schedule. The industrial cooking equipment aboard the ship is built to military specification, meaning it is designed for continuous operation across extended deployment cycles without the kind of maintenance intervals that civilian commercial kitchen equipment requires. The steam-jacketed kettles, the convection ovens, the griddle surfaces, the deep fryers, all of it is engineered for a tempo of use that would destroy conventional commercial equivalents within weeks. But the redundancy goes deeper than hardware. The food service workforce itself is distributed and cross-trained in ways that civilian kitchen operations are not, because a civilian restaurant can close for a sick day or a broken oven. The Gerald R. Ford cannot. There is no closing time. There is no calling a repair service. There is no ordering new equipment from a supplier 2 days away. Every failure must be absorbed internally by people who have been trained to work around it, adapt to it, and continue producing 18,000 meals per day, regardless of what has gone wrong. If this failed during your shift, you would not call for help from outside. You would look at the people next to you and solve it with what is on the ship. The water system is where the self-contained civilization logic becomes most visceral, because water is the substrate beneath everything: the meals, the hygiene, the medical systems, the psychological normalcy of a daily shower. The Gerald R. Ford does not carry enough fresh water to sustain 5,000 people for months. It generates it. The ship uses distillation systems powered by waste heat from the nuclear reactors to continuously convert seawater into potable water, producing tens of thousands of gallons per day in a process that must run without pause, because the buffer capacity is not large enough to absorb a multi-day production failure. The water system and the food system are therefore not parallel systems. They are interlocked dependencies. The galleys need water to operate. The food preparation process requires potable water at every stage. The crew hygiene systems that prevent the kind of communicable disease spread that would devastate a 5,000-person enclosed population require water. If the distillation systems fail, the food system degrades within hours, not days. And this is where civilian logic collapses entirely. There is no municipal backup. There is no reserve tank that buys weeks of time. There is only the continuous operation of the distillation system and the nuclear power that drives it. And every meal served on the Gerald R. Ford is, in a direct and traceable causal chain, a product of nuclear energy converted into potable water, converted into cooked food distributed at scale across a population living in tight quarters inside a sealed hull at sea. The waste system completes the closed loop in ways that are rarely discussed, but are fundamental to understanding how this vessel functions as a civilization rather than a temporary encampment. 5,000 people generate enormous volumes of organic waste, gray water, food processing waste, and biological material every day. On land, a city of 5,000 has a sewage system, a waste processing facility, environmental regulations, and geographic space to manage this. The Gerald R. Ford has none of these. It has engineered solutions to every waste stream. It is because the alternative, improper waste management in an enclosed metal environment at sea, would create biological hazard conditions that would compromise the health of every person aboard within weeks. The food waste from 18,000 daily meals alone represents a significant material volume that must be processed, reduced, and managed in compliance with maritime environmental law, which prohibits the discharge of untreated food waste in certain oceanic zones. The systems that handle this exist because they must, not because they were cheap to install or easy to maintain, and they are connected to the broader food system in the most direct way imaginable. The faster the galleys operate, the more waste they generate, and the waste systems must scale to match the output of the food systems at every point in the operational cycle. The medical infrastructure that supports the food and water systems, and the 5,000 people who depend on them, represents another layer of the self-contained civilization architecture that is easy to overlook. The Gerald R. Ford carries a medical facility that includes surgical capability, intensive care capacity, dental services, and pharmaceutical stores sufficient to sustain a population of this size through months of deployment without external resupply. Foodborne illness in a population of 5,000 in an enclosed environment with no hospital network to offload patients to is not a public health challenge. It is an operational emergency, a contamination event in the cold storage system, a failure in the food preparation temperature protocols, and a breakdown in the hygiene systems that govern the galley workforce. Any of these could produce a communicable illness event that would move through 5,000 closely quartered people with speed and scale that would be catastrophic to operational readiness. The food safety systems aboard the Gerald R. Ford are therefore not procedural formalities. They are mission-critical infrastructure. The temperature logging systems that monitor cold storage continuously, the sanitation protocols that govern every surface in every galley, the medical screening processes that manage sick crew members before they enter food handling environments, all of it exists because this ship cannot call for outside help, and because 5,000 sick people at sea, 600 miles from land, with no resupply and no hospital, is a failure condition with no recovery path. And this is where the escalation curve of this system reaches its most fundamental level, because underneath all of it, the cold storage, the galleys, the water distillation, the waste processing, the medical infrastructure, is the power system. The USS Gerald R. Ford is driven by two nuclear reactors that produce electricity at a rate that dwarfs conventional naval propulsion, and that electricity is the substrate upon which every other system depends. The refrigeration systems are electrical. The distillation systems are electrical. The galley equipment is electrical. The lighting in the food preparation areas, the ventilation that prevents heat and contamination buildup, the communication systems that coordinate meal service across multiple galleys simultaneously, all electrical, all nuclear-sourced, all continuous. If you were to trace the chain of dependencies backward from a single meal served in the Gerald R. Ford's main mess deck, you would pass through the hands of the food service workers, through the galley equipment, through the cold storage systems, through the water distillation process, through the electrical distribution network, and arrive finally at two nuclear reactors operating in the deepest part of the hull, generating the thermal energy that makes all of it possible. The meal is, in the most literal sense, a product of nuclear physics applied to human survival logistics. Most of the 5,000 people eating it will never think about this. That is, in a precise and intentional way, the point. The system is designed to be invisible when it works. The discipline and engineering required to keep it invisible, to make 18,000 daily meals feel routine rather than miraculous, is what the Gerald R. Ford actually is, beneath its weapons and its aircraft and its combat mission. It is a self-contained civilization that has solved, in metal and nuclear energy and human discipline, the oldest logistical problem in the history of organized human effort: how to keep thousands of people fed, healthy, and psychologically intact when the world outside the hull has been completely removed from the equation. What has never been fully examined, however, is how the command and information systems that coordinate all of this across multiple departments, multiple deck levels, and multiple operational tempos manage to do so when communication with the outside world goes dark. And that is a system whose architecture raises questions that the food system alone cannot answer.